Good day, everyone. My name is David Williams, Executive Director of the United States Association for Energy Economics. It gives me great pleasure to welcome you to today's webinar entitled Nuclear Power, Recycling and Advanced Reactors. We are grateful to our moderator, Dr. Isabella Ruble from the U.S. Department of Energy, and our distinguished panelists for today's timely discussion. First, a little bit about the United States Association for Energy Economics. We are the largest affiliate of the International Association for Energy Economics and provide a forum for the exchange of ideas, experience, and issues among professionals interested in the field. The organization produces 2 professional journals, a newsletter, and holds conferences and virtual presentations, along with a host of other products and services you can find on our website at www.usae.org. If you're not already a member of the association, we welcome you to join. A few housekeeping matters in regard to today's webinar before I hand things over to our moderator. First, this webinar is being recorded for those that cannot participate in today's live event. If you have questions for our panelists, please click the Q&A button at the bottom of the Zoom window and type your question. We have allocated sufficient time at the end of this webinar to address your questions. And now I would like to introduce you to our moderator, Isabella Ruble, who is a PhD economist passionate about data analytics, energy economics, and policy with experience in academia, consulting, and government. Isabella currently works at the U.S. Department of Energy in Washington, D.C. Prior to this appointment, she was a faculty member at AUB, George Washington University, and George Mason University. She has worked on issues related to crude oil, natural gas, renewable energy, and nuclear. Isabella, over to you.
Good morning, everyone. Welcome to the webinar, and thank you all for joining today. I'm excited about this webinar because commercial nuclear energy has many benefits, and it provides a reliable baseload electricity, has environmental benefits when it comes to when it comes to climate change, and advantages when it comes to national security. The aim of this webinar is to provide some insights into the nuclear fuel cycle. In the US and France, and show some of the benefits of reprocessing spent nuclear fuel, get some insight into the current state of development and commercialization of microreactors in the US. I will briefly introduce each speaker, and after the 3 presentations, we will take questions from the audience. So our first speaker is Dr. John Carmack. John is a senior technical advisor to the Assistant Secretary of Nuclear Energy since March 2018. He previously served as National Technical Director for the Department of Energy's Office of Nuclear Energy Advanced Fuels Campaign. He has a long-standing career in nuclear energy research and holds a PhD in nuclear engineering from the University of Idaho. John, please go ahead.
Thank you, Isabella, and thanks to everybody for joining us today. My job today is to provide a very quick overview of nuclear fuel recycling and how it works. And then to offer the opportunity to everyone to ask questions about nuclear fuel recycling that you never knew who to ask or never had a place to ask those questions. So first, let me just start with the considerations for recycling of nuclear fuels and materials that we have in our nuclear power reactors around the world. Why would we recycle? There are many commercial drivers that could come to bear that would drive us to consider recycling. The resource availability and sustainability drivers. There are, optimization of our resource that we're extracting from our earth and how we utilize them to produce energy. Reduction of waste. And then also the societal value of recycling, just making the maximum use of the resources that we have available and making sure that we use them in a sustainable and responsible way. Why don't we recycle today here in the United States? Primarily, it's economics. Uranium is very cheap, and so there's not much driver to drive us to recycle our nuclear fuel right now. Now that may change in the future. And then also there are many influences that are from a proliferation perspective. There's a perceived risk of diversion of the nuclear material if you are recycling. And I say perceived because there's actually been no diversion of nuclear material from commercial nuclear facilities around the world today. Diversion has happened in other primarily military uses of nuclear materials, but not from the commercial industry. So what we'd like to ask today is, why shouldn't we recycle? And to this end, advanced reactors of the future may give us the ability to change that consideration in our system. So first, let me start with what we do today. Our current open, what we refer to as an open fuel cycle, utilizes less than 5% of the available energy resource that we extract from the earth in the uranium resource. You typically, in our light water reactors that we find today around the United States, our nuclear fuel that fuels those reactors typically spend about 3 years in the reactor producing power, and then they are removed and placed into a cooling pool for about 6 months. And then the fuel assemblies are removed from that cooling pool and then placed into what we refer to as a dry storage environment in a cask assembly. And typically that is stored on pads, very simply. But in that process, we only utilize about 5% of the available energy resource. If you look at the graphic on the right here, the primary bulk of the fuel that's left over is still over 95% uranium. We can take that resource, recycle it, and use it in advanced reactors of a variety of types, and continue producing energy from that resource. Now, if you look at the left side pie chart, these are the things that are that are produced when the fuel is actually operating in the reactor, and all of these components have some impact or usefulness in a recycling system. For instance, the americium, neptunium, and curium can be recycled back into a reactor and destroyed. The plutonium can be recycled back in the reactor and used to produce energy. Some of the other parts and pieces that are produced still will not be able to be recycled, and so they will represent waste products that we still do have to provide for long-term storage. So, but the primary bulk of the remaining fuel can be recycled back into an additional reactor. Oops, excuse me. So just to give you an idea of what's involved in actually recycling fuel, when you're finished with the fuel, you have the spent fuel rods, the used nuclear fuel. It goes through an initial processing that removes the fuel from the structural components of the fuel assembly. Some of those things have to be disposed of as waste, but the largest fraction of the material is then dissolved into, typically in this process, an acid chemical process. And then it goes through some high level and extraction processes to separate the uranium from the plutonium and obtain a finished product that's of higher purity that can be fabricated into new fuel assemblies and then placed into another reactor for power production purposes. There are many different types of recycling processes that have been investigated, developed, or even implemented around the world, but typically they do have some kind of chemical process and separation associated with them. These systems are usually required to be in what we refer to as a containment building that protects the workers and the environment and surrounding populations from risk of exposure to the radionuclide species. And we refer to those buildings and facilities as hot cells typically. There are a few of these systems around the world today, and Cecile Evans, the next speaker, will be talking more in detail about some of the facilities and processes that are utilized today in France for this purpose. So advanced reactors in the future that will be able to recycle this type of material are varied. This graphic shows a selection of advanced reactor systems, and I've given you a reference to an organization called Generation 4 that has much more details of these reactor systems and how they work and operate. But effectively, here in the United States, there's a lot of research going on. Over 35 to 40 companies are actively investigating, designing some of these advanced reactor types. And in some form or fashion, all of these reactor systems either utilize fuel to a higher capability or are able to recycle fuel back into their systems, or are able to achieve a high level of use of their fuel to achieve a much lower amount of waste production. Typically, these systems are higher energy, higher neutron energy, so they're capable of taking the recycled fuel materials into them and utilizing it as fuel itself. Typically, also, these reactor systems are not light water reactor systems that we have today. They typically use other coolant systems for maintaining cooling through the active reactor core region. But that also gives us the ability to extract more energy and at higher efficiency from some of these systems when compared to our standard light water reactor systems that we know today. So just to summarize, and we'll talk about a little bit about more in detail advanced reactors in Alex Gilbert's presentation, but advanced reactors in the future will utilize their fuel much better than the current reactors that we know today and will produce less waste. Typically, in a fully closed fuel system where reactors are producing their own fuel as well as burning their own fuel, we can expect up to 160 times more energy extraction from the fuel resource and up to 20 times less waste produced from those reactors than our current light water reactor fleet. And that depends on, of course, on the reactor type that's chosen, the fuel cycle choice and mix of technologies that's utilized, and then the recycle strategy that's chosen. I've given you a reference to a very technical report that was published in October of 2014 that looked at the large number of variations of fuel cycles that are potentially available in the future that could potentially have a mixture of different reactor types that are interacting with each other and producing fuel and burning fuel from each other. So there's many different variations that were studied in this report for what future nuclear fuel cycles could look like. And so did a lot of the studies for the data that we utilize to understand future nuclear fuel cycles. So with that, I'll close, and I think we can move on to the next presentation.
So our next speaker is Ms. Cecile Evans. Cecile joined Orano in 2002. Cecile had held various positions at Orano over the years. She is currently Orano's marketing and strategic development director, responsible for the company's used fuel management, R&D, and waste management activities. She is also the chair of the nuclear fuel cycle section of the French Nuclear Society. Cecile, please go ahead.
Good morning to all. In my presentation, I will share elements overview of the French nuclear fuel cycle, highlighting the benefits, and also giving insight on the economics of the different fuel cycle options. So I will start with the French nuclear fuel cycle. As you probably know, we currently have 57 reactors in France. One has just shut down at the beginning of this month. So we have 62 gigawatts electric nuclear capacity, which represents around 70% of the French electricity produced. France has implemented a recycling or closed option strategy with mono-recycling strategy currently implementing, using the infrastructure which are mainly located in France, both for the front end as well as the back end with the recycling platform, which is located at La Hague and Melox facilities. So currently the spent fuel is reprocessed at La Hague facility, and the reusable material, especially the plutonium, is transformed into MOX fuel, which feed 22 reactors in France and provide 10% of the French nuclear electricity. The repu is currently stored and will be recycled again in the next few years, which will allow to provide 25% of the nuclear electricity providing from recycled fuel. The used recycled fuel, MOX and aerofuel, are currently stored underwater for future use. So the French government has recently confirmed the mono-recycling strategy, and it will continue to be implemented at least until 2040. The main assets used to perform the spent fuel recycling in France are the Orano recycling platform with the La Hague reprocessing plant and the Melox fabrication facility. It has been in operation for over 40 years as France implemented its recycling since 1987. It provided services for both the French fleet as well for the some other countries. So far, we have reprocessed over 35,000 tons of fuel in La Hague and manufacture MOX fuel, which has been loaded into 43 different reactors worldwide. We are also implementing continuous innovation and R&D program to enlarge our capacity and industrial scope, providing services which for different type of fuel, LWR fuel with higher burnup currently implemented in reactors, but also research reactor fuel and advanced reactor fuel type. We also have been making progress in the confinement of the final waste to be in place in the future geological repository. And for us, the recycling represents a key asset to address the back-end challenge. On this slide, I'd like to highlight the benefits accomplished so far for the French nuclear fuel cycle. So the recycling strategy implemented allowed us to save almost 22,000 tons of natural uranium, so approximately 3 years requirement of the French fleet. And it also gave us reinforced energy independence when we consider the reprocessed uranium stockpile, which is currently stored in France and represent 2 years of strategic stockpile for the French fleet. The reprocessing of fuel allowed us to save over 20,000 tons of spent fuel storage capacity, and also reducing the final waste, which will be disposed in a deep geological repository. The volume compared to open cycle is reduced by a factor of 5, as well as the radiotoxicity is reduced by 10. We have developed an engineered confinement specifically designed for storage, transport and disposal requirements with a high level of durability, allowing to ease the design of the geological repository, its future operation, as well as optimizing its cost. So when we look at the future, the current mastery of the reprocessing and recycling technologies not only brings major social economic benefits to the country with long-term, high-level qualified jobs, but it also represents a strong enabler to move to advanced fuel cycle. Therefore, the government, together with the French industrial stakeholders, confirmed the development of an R&D program, which will support the closure of the nuclear fuel cycle. First, maintaining the perspective of advanced fuel reactor implementation in the second half of the 21st centuries, and focusing in the middle term in an option or study of an option on multi-recycling of plutonium in current technology of reactors. Now, if you look at the fuel cycle options and the overview of the system, we can talk about two main nuclear fuel cycle options: open cycle or direct disposal, and closed cycle with recycling technologies. When we look at the back end of the fuel cycle, we can say that independently of the option, the overall costs will be a small portion of the total levelized cost of electricity. However, when we need to assess the different fuel cycle, technical and economical performances, we need to look at the fuel requirements as well as the used fuel inventory management. So fuel products to meet the reactor requirements, whether they are based on natural uranium or based on recycled fuel, and this will depend on current fleet technology, but also future fleet technology, considering a small modular reactor as well as advanced reactor, and also the back end of the fuel cycle with interim storage, final conditioning or encapsulation required to directly dispose the spent fuel in disposal when you talk about open cycle, or reprocessing and recycling, and disposal of the vitrified final waste for the closed cycle options. Beyond those elements, used fuel management program will last on a very long time frame, a century at least, even more. And they need to take into consideration multidimensional criteria. First of all, the national policies and safety, but also environmental regulations, but also the long-term energy mix plan with the installed and future nuclear capacity, or in some cases, nuclear phase out. Also the availability of the resource, and specifically natural uranium resource. We need also to consider the social support, existing infrastructure, whether they are indigenous or shared capacities, suitable geology to dispose of the final waste, and also those criteria may evolve in the time frame of the spent fuel management program, and they will potentially change over time. There are a lot of studies looking at the economics of the back end of the nuclear. In this slide, I put one of the latest one, which is OECD NEA study, which was released in 2013. The main output of this analysis shows that if we consider the three options, direct disposal or open cycle, partial recycling, which is the current strategy implemented in France, and or multiple recycling with advanced reactors. Comprehensive fuel cost needs to be considered, not only back-end costs. And the differences among the three fuel cycle options are close and within uncertainty margin. Also, those studies are based on idealized system, and assessment will need to be implemented in detail, taking into account the specific national context. So on the long term, the useful management system involve potentially multiple decisions, and which will be need to account for uncertain factors, especially due to the very long time frame of the program, and no fixed scenario can be decided once and for all. You probably need to account for uncertainties as well as opportunities that may arise with technological innovation. This slide just illustrates that the two different options are lasting for a very long time frame. A part of the program are currently industrially in operation. No disposal is actually fully constructed, no in operation worldwide. So some uncertainties remain, and risk and uncertainty may evolve with time. To conclude my presentation, I'd like just to show some highlights, taking into account both the challenges and the drivers on the spent fuel cycle option. First of all options will require some storage solution. Secondly, handling and transport of spent fuel will be, or used fuel will be necessary, as well as access to geological disposal capacity to in place ultimate waste. Recycling is a key asset to reduce risk, but also increase flexibility and potentially financial predictability. Adaptable schemes may provide flexibility and allow to move to a recycling system in current technology of reactors, but also future technology of reactors. Assessment of the overall cost is necessary, and we need to account for uncertainties. So far, a lot of studies have been based on standard classical NPV DCF analysis, but looking at the time frame, we probably need to consider some innovative assessment to look at the economic of the overall system, to take into account the risk as well as the flexibility of the options, using systems such as a real option alternative, which can be developed to assess the economics of the two different fuel cycle options. Thank you very much for your attention.
Thank you, Cecile. And now we're coming to our last speaker today, which is Alex Gilbert. So Alex is a complex systems researcher who focuses on governance and market design for energy, nuclear, and space technologies. He's a project manager at the Nuclear Innovation Alliance, where he advances nuclear policies and policy reform for advanced reactors to support climate mitigation, with a focus especially on international licensing harmonization. Alex is also a non-resident fellow at the Payne Institute at the Colorado School of Mines. Alex, please go ahead.
Thanks very much for the introduction, Isabella, and thanks as well to USAEE for hosting this event. The last two presentations were really interesting and useful, and I hope that this can kind of answer some questions about where these fueling innovations in closing the fuel cycle could impact the reactor side. So today I'm going to be talking about microreactors. As the name implies, these are very small reactors. Historically, we've had microreactors, but they've been relegated to research roles. What we're looking at now is actually commercial microreactors for power and other type of energy generation. So to start, what are microreactors? If you look at the existing fleet of commercial nuclear reactors, they are almost exclusively light water reactors. They're all very large, at least 1 gigawatt thermal, usually around 3 or more gigawatt thermal, which means the unit sizes for these are among the largest unit sizes in the electricity world. There's a number of reasons for that. When you get to that size with a light water reactor, you have the highest efficiency level for your fission. You also have cost efficiencies related to just the large size, and you can get economies of scale. The problem is that when you get to that size of a project, not just in the nuclear world, but in the electricity world and generally in mega project world, you start hitting diseconomies of scale. The project takes so long to build that you can have snowballing effects from relatively small delays. And because you're building such a complex machine, you have higher risks of both cost delays, but also project cancellations. So we've seen this most recently in the United States with the AP1000s. We've had 2 projects canceled, 2 seriously delayed at the cost of billions of dollars. And that has effectively, in a lot of ways, paused any eventual nuclear development of large reactors in the United States. So in response to this, there is a large amount of innovation, both in the United States and abroad, that is looking at how do we get past those construction issues, while also addressing some of the other concerns that we have with nuclear from a technology and a policy side. A lot of talk over the last several years has focused on small modular reactors, which are usually envisioned to include advanced light water reactors. But there are also a number of advanced designs that are in the same size range in terms of megawatts. But microreactors are a distinct branch of advanced reactors that are emerging right now. They are typically considered to be less than 10 megawatts electric or about 30 megawatts thermal. And most designs are going to be, that are currently released, are all non-light water reactors. So why do we want to pursue microreactors? The first and probably one of the most beneficial is that by reducing the size of your unit by such a great amount, you're talking 2 to 3 orders of magnitude, it simplifies the overall process of constructing and operating these facilities. There is one really big advantage, is that when you get to this size of a reactor, you have reduced the amount of surface area compared to the fission rate in such a way that you actually are able to use passive heating. That essentially there is enough surface area that the heat will dissipate naturally in most situations. So you don't need to have a complex active cooling system. The best analogy that I've heard to really understand why do we want to have these type of machines is that they're really simple. A conventional 1 gigawatt reactor is like an 18-wheeler. To do an 18-wheeler, you have to have all sorts of systems involved, complex braking systems. You have to test a lot of different things because there's a lot of different ways that you can have an accident with an 18-wheeler. A microreactor is closer to a motorcycle or even a bicycle. It's going to be a lot simpler construction. There's going to be a lot fewer failure points. Because you are going to such a small scale, you are going to have, in general, an increase in your relative cost per megawatt hour. That means that if you're trying to compete with a conventional nuclear plant, you might not be able to with a microreactor. In fact, you're unlikely to in the near term. But there are a number of reasons that these units could be applied in situations that nuclear has never been before. And so that gets us to our use cases. The first one is something that we're looking at a lot right now and initial projects are focusing on, and that is as demonstration reactors. For years, even though advanced nuclear has been talked about, there's been concerns that these are not really real reactors. There's no ones that are built, none operating, and until they actually are, they're not a feasible climate solution or a solution to other energy concerns. So as we'll go over the next couple slides, there's a number of reactors that are demonstrating that advanced reactors are possible, that we can build these in compressed timeframes, which is something that would be really useful on the commercial side, and really to kind of prove out a number of different innovations that we're working on in the field right now. Otherwise, there's a number of really specialized applications. The biggest one that I think could be a game changer is that because these units are so small, they allow nuclear to be a distributed energy source for the first time. What that means is that historically, the only entities that really could use nuclear power plants because they were so large are going to be very large scale utilities or large consortiums of smaller utilities in co-ops and municipalities, which poses all sorts of political concerns and questions. That factor is one of the things that contributed to the cancellations of the AP1000s in the South. So if you are a community that only has 1,000, 2,000 people, you have other types of distributed energy resources or other types of energy needs, microreactor gives you the option to use nuclear power for the first time, and potentially it can be a preferred option to the alternatives, which in a lot of cases are going to be diesel power. Finally, there's some specialized applications that are interesting from the ability to expand the applications of nuclear. Space reactors, which we'll talk about in a sec, but also mobile reactors. So you can design these reactors because they're so small to be mobile. You can fit them the size of a shipping container. And that's particularly interesting for the military right now because they have some severe energy concerns. They've done studies and found that a substantial portion of casualties in Iraq and Afghanistan were related to energy supply and fuel convoys. And so they're looking at trying to use microreactors as a way to create resilient energy resources that don't endanger their supply lines. So Kilopower is a really interesting project that in many ways has proven that advanced reactors can be built. So this is the first entirely new nuclear reactor designed, built, and operated in the United States in several decades. We can do advanced reactors. We've done it. This was a joint project between the Department of Energy and NASA to build a fission reactor for space applications. Space applications are challenging from an engineering perspective because you have a unique environment that poses certain constraints. You have zero or microgravity. you have vacuum of space, you have extreme swings in the temperature that you're operating in. And so when the DOE was looking at how do we do the design for this reactor, they really had one guiding philosophy, and that was get an operating reactor built. There was a good special issue of the Journal of Nuclear Technology that went into the entire process around kilopower. And really their design philosophy led to the success of the project, which is they built a demonstration reactor, they operated it, and now NASA has a potential fission option for their missions in the future. One thing to really note about kilopower is the name kilopower. This is a reactor designed to operate in an exceptionally low power output. From about 1 to 10 kilowatt equivalent is the range that they're aiming for. That's about the size to power a house, whereas most reactors are going to be able to power up to 1,000 or more houses. They're closer to the size of a modern wind turbine. And this just shows the flexibility that we now have with nuclear technologies. Now, this is not going to be affordable for commercial applications, but for space and other very specialized applications, this is an interesting option. The next really interesting project that is moving forward, that they're beginning construction soon, is the Transformational Challenge Reactor. This is a project at Oak Ridge National Laboratory, and what they're trying to do is construct the core of a nuclear reactor using additive manufacturing, or 3D printing. That is something what they're trying to do is show that advanced engineering and other types of innovations can be applied to the nuclear field. And the reactor core in particular is a challenging area because that's where some of the most intense physics environments occur in the operation of a reactor. So if you can actually build a reactor core using 3D printing, it's a demonstration that you can probably do so, use 3D printing for any part of a nuclear reactor or nuclear parts. That's something that's really promising when we get to how do we reduce the construction risks for advanced reactors, because if you can have a 3D printer on site as you're going through the construction process and build a part that you might have had to wait 2, sometimes 3 months to have delivered to you, that can reduce your risk of having a time overrun and hence the cost overrun. Again, one thing that's really interesting about the TCR project is that this is on track to be built and operated by 2023. It was approved and started really last year in 2019. That 4-year time frame, even for a government project, is something that is an important precedent to start for the advanced reactor community. And it also shows that we can maybe start addressing some of those cost challenges. There are a number of commercial projects that are also looking at advanced reactors. By far, what's considered the industry leader is Oklo. They have a design for a 1.5 megawatt electric facility that has now entered into a combined construction operations license at the NRC. Depending on the time frame for that, they could potentially have an operating reactor by the mid-2020s. It depends on how the regulatory review goes and how the construction process goes. But that's really exciting because that means that we could have an advanced reactor relatively soon. And their design is specifically targeted towards smaller communities, particularly in the Arctic, that need to have power that's reliable and are currently relying on diesel. Otherwise, another good example is Westinghouse, which is one of 3 reactors that's working on the mobile reactor program for the Pentagon. Their Vinci design is looking at entering into an NRC application soon. I believe they're in pre-application. But overall, there's anywhere from 12 to 14 companies in the United States that have maturing microreactor designs. There's more abroad as well. So this is an area where companies are looking at as an active source of innovation. The question is, will these things be competitive? And that is really the most important long-term question. Once we can build these things and show that they can be built, can they actually compete and be deployed in markets? This graph is from a study conducted by the Nuclear Energy Institute. They reviewed designs from a number of microreactor developers and created a generic microreactor. And they looked at it under a number of different cost and customer profiles. What they found is that the initial project is going to be more expensive, as it always is. But because of the size of the projects and because of the relatively short time frame involved, you can scale these up quickly. And you can start getting economies of scale and learning from having more and more of these units built. And so if you look at this graph between units 1 and 10, you have substantial cost declines in the cost per unit. And what that means is that over time, as these expand and grow, you can actually see a large number of demonstrated units that are having clear cost performance, and that's necessary to start breaking into a lot of markets. Another thing that's really useful about this graph is it shows the different target segments that microreactors can serve. You start at the very top of the remote Arctic communities, which have some of the most challenging energy needs. They're in areas that they require both heat and electricity at low price. But then going down all the way to the Alaska Rail Belt, these are areas that primarily use diesel. Diesel is expensive for these areas. Diesel is dirty. And it's also something that does have energy supply constraints. So you have to rely on a bunch of tankers and other sorts of transportation bringing it to you. And that's an energy security or resilience concern. So these areas are likely first adopters of microreactor technology, and they can really prove it out. The final thing to point out about this is that in each of these cost case examples, microreactors never really get to a cost competitive point with the US grid. That is to be expected because they are so small. And it's really emphasizes the fact that these are distributed energy resources. These are not meant to be grid scale competitors, at least yet. To connect with the previous two presentations, microreactors have several notable features on the fuel side. Now, each of the companies is pursuing a different innovation in fuel type. Generally, though, these line up with what's happening on the advanced reactor side. Most of them have limited refueling cycles or lengths. Currently, most reactors refuel about every 18 to 24 months. Some of these are much longer. Oklo's plan is to have a reactor that operates for 20 years and doesn't actually have a discrete refueling. They just replace the core. It has a number of energy security advantages, but also really helps with how you're designing the fuel cycle portion of your energy system. Most, if not all, of the reactor designs are going to be fast reactors. And finally, on the fuel selection, in addition to TRISO, a lot of these reactors are looking at using HALEU, high assay low enriched uranium. And that really helps when you're looking at the fuel efficiency of the reactor and to enable those long time frames. Now, in terms of commercializing, the technologies are entering the demonstration phase. The next phase will be commercialization. First, it's going to be really important for the advanced reactor industry broadly to have any commercial advanced reactor working, even if it's a microreactor. If one company does it, other companies can actually raise money off of that, and it allows us to really get the innovation steamrolling. But nevertheless, finding initial customers is going to be a challenge. The traditional business model for reactor vendors is that they build the reactor for another operator that actually owns it. And so in the US, that means that utilities have traditionally owned the reactor that they have built from another vendor's design. That's not clear that that can be applied as well when it comes to microreactors. In Oklo's case, Oklo is considering a build, own, operate model where they actually will own it and work as an independent power producer to sell their electricity. There's a number of reasons why that might be better from a microreactor perspective. Finally, when we look at what does this mean from the policy side, there are a number of issues that are unique to microreactors. In general, most of these issues are things that we see for advanced reactors generally. But when it gets to microreactors, the first main barrier is going to be licensing. Licensing a nuclear facility is the primary regulatory barrier to operating that facility. You will have oversight over your facility over the entire lifespan. But there are a number of things that you need to get, at this point, regulatory exemptions to operate within the current licensing environment. The number one is that current regulations require you to have an on-site operator. And that makes sense when you have a very large facility that has safety risks involved and also has a complex interaction with the larger electric grid. When you're talking about a microreactor that's a couple megawatts, it's not going to be economic to have an on-site operator in all cases, and it's also not clear that it's necessary just because of how the technology works. So figuring out how to work around that's going to be a challenge. Secondly, the NRC is working right now on a generic environmental impact statement. In order to get a nuclear plant license in the US, you have to go through the NEPA process. It's usually done in parallel to the licensing process, but that can pose issues depending on how that is conducted. And if we can figure out how to streamline that process through a generic statement, we can make sure to protect the environment while also getting these reactors deployed. And so that's probably going to be a good point to end this presentation and go to questions. But my big takeaway that I hope you take from this is that microreactors are here. they're going to be here first before a lot of other advanced nuclear innovations. And they have the potential to be disruptive for the energy system more broadly, but also within the nuclear industry.
Thank you, Alex. That was very insightful, and we got a lot of interesting questions. So I will start with our guest from Europe. And so for Cecile, the question is, the EU depends on nuclear power for about 26% of its electricity supply, and that share is even higher when you look at baseload. How do you see the future of nuclear in France and in the wider EU?
Thank you, Isabella. As you said, the EU is nuclear plant is providing a major part of electricity, and especially low carbon electricity so far. I think we are facing, maybe like in the US, the challenge that is linked to the age of our nuclear power plants, which will require either long-term operation or extended operation time, or will lead to a retirement of some of the currently operating reactors. Beside that, I think EU has a strong climate change target, and we believe that nuclear, together with renewables, will be not opposed, but more allied to target climate change and reach the European target we have set up with the EU. I think if you look at France, the current share of nuclear electricity is even higher. So the government has issued a policy to reduce the target or the share to 50% of the electricity produced, but nuclear will remain a big part of the electricity technology provider in the future.
Thank you, Cecile. That's a very insightful answer. I have a question for John. What is the US experience in recycling so far?
Well, the US actually has quite a bit of experience at the research and development and R&D scale on recycling different types of fuels that are utilized in both the light water reactor fleet today, as well as advanced fuels of the future. The US has did build a couple of facilities that were intended for commercial scale recycling. There was one that was operated for a few years in West Valley, New York. It was an aqueous recycle plant, and I believe it was shut down in 1980. That was the year after the 3 Mile Island accident, and so it's very well tied to the politics and the public sentiment that occurred after that accident in Pennsylvania. So the experience today, the Department of Energy still maintains the ability to perform recycle and separations of nuclear fuels in two schematics. One is the aqueous recycling process, and the other one is an electrochemical recycling process. Those two capabilities exist in the Department of Energy today. The challenge would be if the economics and the intent to recycle fuel occurs in the United States, one of those two processes or a combination of the two could possibly be used in the future.
Thank you, John. I have one more question for Alex. And the question is, can you talk about the geopolitics of microreactors? What are the implications to develop microreactors in developing countries?
So that's an interesting question. And if you talk to certain people in the nuclear policy world, developing countries are an ideal use case for microreactors, particularly for areas that don't have access to centralized electric grids. That's one of the real advantages of having a distributed nuclear source for the first time, is that you can deploy it to areas that currently either don't have access to electricity or energy at all, or have unreliable access. And reliability is particularly a large concern for a lot of developing countries. And so it's an ideal technical solution. The geopolitics is where a lot of the questions and concerns are. And that just has to do with the unique nature of nuclear power and the inherent security risks with radiological materials. Now, these facilities in and of themselves are unlikely to pose any sort of severe meltdown or similar risks. But like research reactors, which we've seen around the world, they do present concerns, particularly around terrorism and theft of materials. So if you're looking at a, say, like a matrix of places where it could be possible, this is not going to be a place where you're going to put in a relatively destabilized country that has high security threats. However, there are many places around the world that are a lot more secure where it could make sense. Indonesia, places throughout sub-Saharan Africa, other parts of South Asia, as well as South America. And so this is an ideal option in a lot of cases. And for certain countries that are interested in going nuclear but cannot afford $1 billion to $10 billion price tag of a large project that has all the attendant risks with constructing a large facility, a microreactor is a good way to start a nuclear power program. It's relatively low commitment, and in building several of these, you can establish the regulatory and also the expertise infrastructure that you need to have a nuclear power program.
Thank you, Alex. John, I have another question for you, and that is, how soon do you see the deployment of fast reactors, and what share do you think they will represent in the U.S. Nuclear fleet in, when they're deployed?
Well, the United States does not have currently a fast reactor under operation. The United States has operated a number of fast reactors over the years, EBR-1, EBR-2, FFTF, and a couple of others. EBR-2 and FFTF were shut down in 1994, but represent a large body of development and research and development data for fast reactor systems. So the U.S. currently, the Department of Energy is pursuing a versatile test reactor, a new test reactor that is a fast reactor, sodium cooled, and would represent a near demonstration scale, but it would allow research and development and demonstration of technologies needed to push fast reactor systems forward. The only fast reactor systems that are available to help the development and research and development of fast reactor technologies are located in Russia and China, and one in India, and all are very difficult to access for the purpose of research and development for the United States technology developers. So that facility, if it were to come online as planned in 2026, I think we are targeting sort of the 2030 to 2035 timeframe for sort of demonstration, commercial fast reactor, advanced reactor systems to come online. The microreactor systems that Alex has been talking about, I think are a little bit earlier than that because of the Project Pele and the DARPA program that supports it has a very fast demonstration timeline. They want to have a demonstration of one of these microreactors by 2023-ish. That could really push forward, I think, the demonstration of advanced reactors, but also, as in one of the questions from George Rowe on in the questions and answer, is then leading to the integration demonstrations. I think after the first microreactors are demonstrated under, say, this DARPA DoD program, you would naturally see those move to demonstration of application and use cases, coupling to water desalination plants, thermal processes, industrial, urban, and community needs and loads, I guess. So I think, so just to sort of clarify, I think we may see, if successful, microreactors in the 2023 to 2025 timeframe, and then advanced reactors in the 2030 to 2035 timeframe.
Thank you, John. So I think we can have one more quick question maybe, but then we're basically out of time. That question is probably for John too. Are fast reactors needed to handle the recycled fuel? Yeah.
Yes. The power of the fast reactor compared to our standard light water reactor, thermal reactor today is fast reactors can take a large variety of composition and fuel compositions. So you can have a large variety of different fuel compositions even in the reactor at the same time, whereas a light water reactor that we have today, that we know today, requires a very narrow fuel composition, a very precise fuel composition in some regards. It doesn't handle sort of the recycle of waste products into its fuel very well, but a fast reactor is really much more amenable to achieving that. And so we see, I think if you look at if you have a transitional system where you have some light water reactors and some fast reactors, you end up needing about a fast reactor for every 7 light water reactors to fully recycle the light water reactor fuel in a closed fuel cycle. But eventually you're going to want to transition to a fully fast system for fully closed fuel cycles that are completely sort of producing their own fuel as well as destroying their waste products. And so that would be, in the long term, probably, 2050, 2060 sort of time frame where you would see a need to have consideration for, transitioning away from the light water reactor technology in a fully closed fuel cycle system.
Thank you, John. And with this, I think we conclude today's webinar. I will give the word back to David.
Okay. Thank you very much, Isabella, and to our distinguished panelists for an outstanding webinar. I truly enjoyed this, learned quite a bit. So, these topics, they're ever evolving, which only means that we need to provide more content on this to our membership. So we're very, very grateful. For those listening or not, you want to pass on to your colleagues that we have recorded this. It will be on our rewind station later on this afternoon. If you're not a member of the association, we welcome you to join. Check us out at www.usaee.org. Thank you for attending, and I officially close this webinar.